Okay, now, so all the homework assignments for the remainder of semester have been created and posted in Lumen and therefore in Canvas. So there are 13 assignments total. So what I decided to do is, when I go to compute final grades at the end of semester, I'm going to drop the lowest homework assignment. Now, one thing I want to point out is I've not yet implemented this in Canvas. And I'm not going to do that until I go to compute grades at the end. Because if I put that rule in Canvas now, it'll artificially inflate your homework grade and make you think that you have a higher grade than you actually do. So I just want to make sure that whatever grade you see in Canvas is less than or equal to what you have. That way when I drop the lowest, you'll get a little lift. Okay, also, we're approaching the end of this particular module. We're gonna finish that this week on all the equations of lines and planes stuff. And then there'll be module 4, which is on parametric curves, polar coordinates, and conic sections. Conic sections is the last homework, and I'm not going to include any questions about it on the final. So I'm putting it up as a candidate for your lowest. If you get to the end of the semester and you just have run out of gas, don't have enough for one more homework after doing the previous 12, then that could be the one. Or if you want to try it anyway to maybe boost your homework grade, that's your choice. Okay, now I'm going to continue talking about the problem of determining whether two lines intersect and focus more on the linear algebra things. But I don't think it'll take terribly long to do all that. So we certainly have time for any homework questions. One thing that just came up. On homework 9, problem number 17, gives you two vectors, A and B, whatever A might be. And what I normally do in the notes, and what happens generally in homework problems is vectors should be formatted using angle brackets. And I use parentheses around the list of numbers to indicate a point in space. So the way the question is written is a little bit misleading. You're supposed to work with it's problem work with two vectors, and maybe it should have been written in that way. Now for the answer, the answer is a vector. And the homework system will require you to input using the angle brackets instead of parentheses. So inconsistent with what they themselves put in the question. So this is what happens when you let anybody write questions. Never know what you're gonna get. So, I thought about writing my own questions and no. The process is way too involved. But unfortunately, it doesn't give me a way to go in and fix things like this. Okay, so are we sure that there are no homework questions now? Oh, you do have one. Okay. Yes.
These silly, but I was confused on 5.
Number 5. Okay. Oh, this one for a graph. Okay. So. Okay, so. Oh, you were asking about this one too, or? Okay, all right.
So, yeah.
Okay, I remember talking about this one not too long ago, but well, so from a process for it. did you catch that from last class or?
The process for number 17.
Yeah, because that's. So that's a question where we give you. Two vectors and find a unit vector. Okay. So. We take our cross products. We get a new vector C. And then. You divide it by its magnitude, which makes it a unit vector. And then. This vector that you get. If a Z component is already negative. That's your answer, that's the vector you input. Otherwise, you negate all the components of the vector, is that what you did? Yeah. Okay,
I have it written down somewhere.
what? Oh, okay,
I don't have my notes.
okay, well, let me know if you continue to have trouble with that one. For number 5. Alright. So what they've done is. Plotted a couple of vectors. So then what you need to do is use the hash marks. Find out what the coordinates of a vector are, the components. So for example, under the graph I see on my screen, this vector is minus. Oops, I have this drawn wrong.
So you just take the point at where it's at, where it ends?
Yeah,
Okay.
and then take the top product of those two. Okay, any other?
On 18.
18. Okay,
Just since they give you the points, I just wasn't sure which, I mean, I know you can find the vectors.
okay, you have to be careful about which. Yeah, yes, you pick any pair of points and find a vector between them. But you have to make sure to pick the right one. So, that's why it's, and I would actually recommend. Drawing the points, because. So if you. Actually, I would suggest finding the point that has the smallest x coordinate. So you know that's a point to the left. And then. The thing is, you have. These possibilities for vectors come from that, but you want to make sure to not include that one. So the visualization can help to make sure that you want 2 adjacent edges of a parallelogram.
Okay, I think I was just overthinking it because there's only 2 points instead of 3. I was trying to think cross product, but you can just.
Oh, okay. Wait, 2 points instead of 3?
Well, I mean, like 2, like an X and a Y instead of X, Y, Z.
Oh, right, okay. Yeah, so okay, well, that's what we're talking about anyway. So if you're given 2 vectors that are in 2 dimensions. And as for a cross product, you can think of it as having it as 0 components. Then what will happen is when you go to compute the cross products, because both of these vectors sit in the XY plane, and the cross product has to be orthogonal to both of them, the first 2 components of a cross product will just turn out to be 0. And then you'll just go ahead and do a third one. And then, now, since this is a problem for area of a parallelogram, you're supposed to take the magnitude of that, but that's just taking the absolute value of that. Anything more? Okay. Yeah. So now take a closer look at the problem that I touched upon last time of determining whether two lines in three-dimensional space intersect, or are they parallel, or are they skew? Okay. Now, let's suppose you have two lines described by parametric equations. Sorry, to notation on the fly. Okay, so that's parametric equations for line number one, and then similar parametric equations for line number two. Okay. So to see if they intersect, you equate x's, y's, and z's. But you have to use different parameters for each line. It's customary to describe a line using a parameter t. But what I'm going to do for line number two here is wherever we see t, I'm going to replace it with f, which is what I should have done the first time. But chances are, if you're given two lines in a homework problem, we might just happen to describe them using the same parameter. But the two lines are independent of each other. That's why the letters from a parameter have to be different. So if I set the x's equal to each other, then I have one plus b1b equals a2 plus b2s. That's for x. And then I do the same thing for y. b1 plus b1t is equal to b2 plus b2s. And then z, I have f1 plus g1t is equal to f2 plus b2s. So what we have here are a system of three linear equations, but in only two unknowns, s and t. So if we can find an s or t that satisfies all three, the lines intersect. Otherwise, they're either parallel or skew. I mentioned how to determine before doing any of this if the lines are parallel. If a vector consisting of the coefficients of t or s are parallel, so that vector b1, d1, G1 is parallel to a vector of the other direction number, it's B2, D2, D2. Then we can just say the lines are parallel. So for the rest of today, we're just going to assume that they're not, because you just check that. If so, if that works out, you're done, you're done. Otherwise, your job is to sort out whether they're intersecting or skew. Those are the only two possibilities. Okay. Now, the approach I described last time was, does you have, in a way, too many equations, you can just choose any two of them and try to solve those and see if your solution satisfies the third one. So I'm going to focus on an abstract system of this form with unknowns S and T. AS plus BT equals U. BS plus BT equals V. So these are equations you would get from choosing any two of the three. Okay. Or you might not be able to solve them. Or there's no solution. Or what's the other possibility? Either a unique solution or what? If there many solutions. All right. Okay. All right. So what I'm going to do is, for now, I'm going to make an assumption about these coefficients that you get of S and T, A, B, C, and D. I'm going to assume that one of these is non-zero. So in other words, that there's at least an S in the system of equations at all. Because if not, then that makes things simpler in a way. Because right now we have a system of equations in two unknowns. So we're going to assume that those unknowns actually are there. Okay. So what you can do is what you can think is, if you are taking or have taken linear algebra, forming row operations. Actually, in this case, it's a single row operation on the system of equations right here. What you get is the following. The first equation unchanged. The second equation, you can eliminate S from it. And you get this, AD minus BC times T is equal to AV minus CU. So this system is equivalent to the original system right here. It's just that it's a lot simpler to work with because now this second equation depends only on T. So you can just go ahead and solve that second equation for it. So if this coefficient of T right here, AD minus BC, is non-zero, which is why I made this assumption up here, because otherwise it definitely would be zero. Then I can just give you formulas for T and S right now. So T turns out to be this expression, AV minus CU over AD minus BC. And then you can take this expression for t and substitute it into the first equation, and then you can go ahead and solve for s. So your work is done, pretty much. So, and what we have here, this is an instance of having a unique solution. Right, so these are the possibility that the two lines intersect. Because in terms of the x and y components, like if I chose the x and y equations from this system and worked with that here, that's what would be happening. If you look at just the xy planes, the lines do intersect, but you also have to check z. So I would plug these two values of t and s into the third equation. And if that equation is also satisfied by these t and s values, then you're done and the lines intersect. Otherwise, they're skew. The actual algebra for working this out is given in the notes. This expression right here, AP minus BC. Yes. Thank you for sparing me asking the question. So it's so I can write this system in matrix vector form. A, B, C, D times the vector S and T is equal to the right-hand side values U and V, and AD minus BC is equal to the determinant of that matrix, and that's when it's, you need that to be non-zero to ensure that there is a unique solution to this system. So that's the nice case where everything works out beautifully and you have a unique solution. Questions so far? Now, I need to talk about cases where things do not work out as nicely. But before I do that, and don't worry, I will be doing a few examples of all this afterwards. This is one of those good to know things. It comes up in a variety of classes. If you have a system of two equations, two unknowns, like I just wrote down there, I'll just repeat it here. I'm going to call this a matrix A. This is a vector, S it's of unknowns, I'll call it X. And I'll call this vector of right-hand side values W. Normally I'd use B, but B's already been used. Okay. If a determinant, so just lapsing into linear algebra for a bit because I can't help myself. If you have not taken linear algebra, don't worry about this. I'll come back to how for you resume in a moment. So the determinant of this matrix is non-zero. The solution is following a vector W, which consists of X, which consists of S and T, is given by the inverse of A times the vector of right-hand side values. And in this case of only two equations, two unknowns, there's a nice formula for it. Who knows the formula? But someone here does. What's the formula for the inverse of this matrix?
Just divided by the it's called magnitude.
Determinant.
Hey, John.
Yeah, you have one over determinants.
Which A, B, and negate the B and C.
Yeah, A and D. Yeah, you switch the diagonal entries, negate the off diagonal entries, and that's multiplied by the right-hand side values. And that's, so the formulas that I wrote over there, that's where they came from.
We do not need to know that, right?
Right, I'm just thinking that it's, depending on whatever math classes you take in the future, it's good knowledge to have. Okay. Oh, same formulas I wrote over there. As you see, there's so many classes that I teach. Where you wouldn't expect it. There's often a need to solve a system of two equations and two unknowns. And this just keeps popping up. And I don't, for a given class, that's on something else entirely, like, differential equations, where I don't expect to use it, but then, oh, this comes in handy. So I find myself telling the students in every class, so just, here it is. But if you're never gonna touch on your algebra for as long as you live, if this is your last math class, for instance, which may apply to some of you, then just ignore me. Okay. So. Back to system, I was, well, actually, okay, it's still this system. It's been, I've kept the notation the same. What if it is zero? All right, so you don't have a unique solution anymore. What does happen, and what does that mean for determining if lines are parallel and intersecting or skew? Well, it depends. So. Now. How this came about in the first place is we have. After eliminating s from the second equation. So let's bring that system back. We have this equation here, then we have. T times T is equal to. AV minus DU. Okay. So here's what happens. If. This right-hand side is non-zero. Whereas the left-hand side of this is going to be zero, then you have the contradiction. You have something zero on the left equals something non-zero on the right. There is no solution possible at all. So then, if this is in the setting of determining what's going on with two lines in three-dimensional space, you can just conclude that they're skew and stop. Okay. Another way of putting it is that the system of equations is inconsistent. I meant to underline that word, not cross it out. Okay. So you already concluded before you started the lines were in parallel. There's no possibility of a solution S and T that satisfies these two equations. Then surely not going to get an S and T that satisfies all three. The remaining possibility here is that if it is zero, then the system has infinitely many solutions. Because what happens is that means that the second equation is reduced to just 0 equals 0. So then you go back to the first equation, you have one equation for the two unknowns S and T, so you can plug in anything for S and always get a value of T. Okay. Dang it. Oh. Whatever. Okay. Okay, so, now. All right, so let's replace my notes. Okay, now, all of this was assuming that, if, either one of those numbers, A or C, was not zero. The other possibility is if both are zero, then the system has no S in it at all. All you have is BT is equal to U and CT is equal to V. So now you can solve both these equations for T to get two potentially conflicting values, U over B or V over C. Wait, sorry, it should be a D. Okay. So what happens here is if you get two conflicting values for T, well, there's no solution. Again, the system is inconsistent. So again, for lines, it really means that the lines are skew. And whereas if they are equal, that's again a situation of infinitely many solutions. Because you have this one value for T and S is allowed to be anything because these equations were not imposing any constraint on S at all. So I've covered all the possibilities. And what we have here, we can have either a unique solution for these two equations or no solution or infinitely many solutions. Okay. So what I'll lay out for you now is now that we've seen that these are possibilities. Here's how to proceed with determining what's going on with the two lines you're given. We're given two lines in three-dimensional space after you've equated the X parametric equations, the Y parametric equations, and the Z parametric equations. Okay. So you take the equations that you get from X and Y. So we're going to ignore the Z equation for the time being. So we look at those two equations, and that gives you this kind of system that I've been working with. Okay. So you get something of that form. All right. Okay. So if this expression is non-zero, then you can have a unique solution for S and T. I gave you formulas for them earlier. Those two fractions. And then you substitute those S and T values into the Z equation. Okay. If they satisfy, then the three lines intersect. If they do not, then the two lines are skew. This is what will happen most of the time. But there's this relatively clear-cut path to figure it out. And yes, it definitely will be a question on the final exam. Here, two lines are parallel, intersecting, or skew. If the system is inconsistent, and that happens if this expression is zero and but that expression is non-zero, then you're done. You can include the lines or skew. Okay. You can't even solve the first two equations for S and T. Okay. Last possibility. If you conclude that the first two system equations have infinitely many solutions, you've already ruled out the lines being parallel. The only possibility left is actually the lines are actually guaranteed to intersect. But at this point, you still don't know where. All right, now, the best thing to do in that case is because you got to this point by looking at the X and Y equations, choose a different pair. So choose the like the X equation and the Z equations, or the Y equations, Z equations. Either choice will certainly work because you've already ruled out the lines being parallel. Write it down what I just said. So X and Z or Y and Z. So involve the Z equations. And then, so then you'll be able to solve for S and T, and then you'll know that that's the intersection. Okay. So that's it. That's a process. Questions before I illustrate it? Yes.
How do you know if they're parallel?
Okay, so I guess I think I mentioned at the end of last time. Oh, actually, I wrote earlier. If you look at the direction numbers for one line versus the other line, if those vectors are parallel, the lines are parallel.
You wrote that if F B D G is parallel to B two D two G two, then the lines are parallel.
Yes, it's that. Okay. Yeah, so all of this is, okay, so. Actually, you've already ruled out that they're parallel. You have a question? Okay. Alright, so my first example, I have. My first line. These parametric equations, I'll use S as the parameters, X is 2S plus 3. Y is 4S plus 3. Z equals S plus 1. Then for the second line. I'll have X equal to, I'll use T for this one. 4T plus 5. Y is 5T plus 6. Z is 2T plus 9. Okay. So check whether it might be parallel. You look at the direction numbers for the two lines, the multiples of S. The first line, so 2, 4, 1. Then for the second line, you look at the numbers multiplying T. So we have 4, 5, and 2. So these vectors are certainly not parallel. So now set up a system of equations for S and T, determine whether they're intersecting or skew. One thing that can make things a little easier on yourself is because ideally you want to choose 2 of 3 equations so that you don't have this AD minus BC equals 0 stuff with it, where it's a check out case or no solution if there are many solutions. So I determined that these two vectors taken as a whole are not parallel. So suppose we want to choose the X and Y equations here. So then I'd be focusing only on these components, the X and Y components. If I look at these vectors, so ignoring the Z, these vectors are not parallel either. And that's good. That makes choosing X and Y a good choice, because then my system will have a unique solution. Whereas if I'd chosen the X and Z equations, here I have 2, 4, 1, 2, those vectors are parallel. So I've written this as like, okay, go ahead, choose the X and Y equations, just cause. And then, oh, it doesn't work out, then choose 2 of our equations. But as you examine the ratios of correction numbers up front, so you're going to anyway, to make sure they're not parallel, you can guarantee a good choice of equations out of the gate. So in this case, choosing X and Y is okay. Look at equate the X's and the Y's. So I have for X, I have 2S plus 3 is equal to 4T plus 5. Y, I have 4S plus 3 is equal to 5T plus 6. But then I write this in the form that I've been working with, where I have all the terms of variables on one side and all the constants on the other side. So I have 2S minus 4T is equal to 2. And 4S minus 5T is equal to 3. So in terms of the notation I laid out earlier, A is 2, B is minus 4, B is 4, B is minus 5, just the coefficients of S and T in the equations. And then we have U and V are the right-hand side values, 2 and 3. So then you check. Well, basically, I told you earlier, because I don't need to, but AD minus BC, so that's -4, so we have -10 plus 16. So because it's non-zero, we know that this system has a unique solution. And we have formulas for S and T that come from that we worked out earlier. So S turns out to be BU minus BV over that same quantity, AD minus BC. He is AB minus CU. So then you can work those out. I mean, or you can just go ahead and do elimination substitution in whatever way you prefer. I just figured if you'd like to have fully worked out formulas for S and T, here they are. Depending on whatever way you prefer to work in. So plugging in all of these numbers here, S turns out to be 1/3. T turns out to be minus 1/3. It's just a coincidence that they happen to be plus the negatives of each other. But not something that generally will happen. So these values of S and T satisfy the first two equations. Now we call the equation for Z components. We have all right, so we have S plus 1 is equal to 2T plus 9. Or if you rewrite that, S minus 2T is equal to 8. So what you can do is you can take these values for S and T and substitute them down there. But what happens is we get you get 1 on the left side and 8 on the right side. So this did not go well. So the S and T that satisfy the X and Y equations do not satisfy the Z equation. So we conclude that the lines are skew. So questions about how this one played out. Okay. Next example, our first line. That's these parametric equations. Oh, okay. Second line. X is equals 5, Y is 16 plus 7 equals 5T plus 9. Okay. Now, if we look at the direction numbers, so we have the first one, we have vector direction numbers 2, 3, 4. And then for second line, we have multiples of t, 4, 6, and 5. So these two vectors are not parallel, so the lines are not parallel. But what would happen if I went and chose the x and y equations to try to find an intersection? Yeah, we would get that situation of AD minus BC is equal to 0, because if I focus just on these, that the ratios are the same. Okay, so right. So the x and y equations are parallel. So we'll make a different choice. So instead I'll work with x and z. So for x, I have 2s plus 3 to 14 plus 5. For z, I have 4s plus 3 equal to 5t plus 9. All right, so then I write these in the same old form, so I have 2s minus 4t is equal to 2. 4s minus 5t to 6. Okay. So I have A is 2, B is minus 4, C is 4, it's minus 5. It would be a 6, so you get all your ducks in a row. And here too, I don't have to compute AD minus BC to know that if I look at these coefficients, 2, 4, I think them as a vector, and then this vector, these coefficients 4, sorry, 2 and minus 4, and 4 and minus 5. Sorry, I should include the minuses in these. Both define two vectors in two-dimensional space that are not parallel. So, and sure enough, if I compute AD minus BC, I have 2 minus 4. No. 5 minus. Okay. Got 6 for that. So, so because that is non-zero, we have a unique solution. So then I'll just go through these same formulas. I can go ahead and use with the numbers that I have. Once I plug in A, B, C, D, U, and B from over here, I'm going to get 7/3 for S and 2/3 for T. So I at least have a candidate for an intersection point. But now I have the y equation. I want to make sure that is satisfied. So I'll have 4 is equal to 16 plus 7. Or written this way, 3s minus 6t is equal to 3. So I want to make sure that values for s and t satisfy this equation also. And who could tell me why it's actually not necessary for me to do that to know, but it does satisfy? There's a way to tell without grinding through all the algebra. But compare this equation to this one. Equations for X and Y. Equations, he is both left and right sides are parallel. This equation is just 3/2 times the upper one. So because these values of S and T are known to satisfy both of these equations, and this equation is just a scalar multiple of a first one, it's automatically going to satisfy. So this is parallel. And I'll emphasize here, both sides to the X equation so values of S and T do satisfy this one. That means you can conclude that there's an intersection. The two lines intersect. What could I conclude about the lines if this number here had been anything other than 3?
Will it have skew?
Yes, they would be skewed because this equation would, these coefficients were known to be parallel to these, but it's the right-hand sides that are key. That's why I emphasize that this equation is parallel to on both sides of it. If it had only been on one side, then I would know that these S and T values don't satisfy this. And I can really rule what they're skewed. Because when looking at these two equations for X and Y, you can see from these coefficients here that that AD minus BC was going to turn out to be 0. But we don't know at that point if that means there's no solution or infinitely many solutions. Given this number here would have turned out to be infinitely many. So the last thing to do, now that we know that there is an intersection point, is to actually get it. So you substitute S equal to 7/3 into the parametric equation for L1, or substitute T equals 2/3 into the parametric equation for L2. Doesn't matter which one, take your pick. And that will give you the X, Y, Z coordinates of the intersection point. Because S and T satisfy all 3 equations for X, Y, and Z. Those 2 points have to be the same, no matter which one you plug in. Any questions about this example? All right, a couple more. Well, this next one's a quickie. First line. Second line. Yes, I know all these lines are just small changes of each other, but, okay. So as before, you can quickly check, and see that the lines are not parallel. I won't go through that part again. But. If you take the x parametric equations, the y parametric equations, and you set them equal to each other, then the system that pops out is 2s minus 4t is equal to 2. S minus 2t is equal to 8. Okay. Can anyone tell me how you can make a conclusion about what happens with the lines just by looking at those two equations, not performing any algebra whatsoever?
One side is parallel, the other is not.
Yes, that's exactly it. So because coefficient of S and T find parallel vectors, that tells you the determinant A B minus B C is going to be 0. So that means no solution or infinitely many solutions. Which is it? You check the right hand side. So I can get these coefficients from the first ones by dividing by 2. I don't have the same ratio over here. So you think of all the numbers on both sides of the equations as vectors, are they parallel? If so, infinitely many solutions. If it's parallel, on taking both sides into account at once. Otherwise, we have a situation of no solution. So you need one equation, both sides of it to be a scalar multiple of the other. If so, that's infinitely many. You don't have that here. There's no solution. Don't even have to look at the z equation. You can just conclude the lines are skew and stop. I think we're all in favor of algebraic solutions. Okay. Oh, wow. Seems to have a duplicate here. Yeah, the very last example in the notes are, that I haven't done yet, is the exact duplicate. Not entirely, like the approach is a little bit different. But basically, the situation like this, where you write out the equations for x and y and see, oh, it's parallel on both sides. So infinitely many solutions, so we just look at the x and z equations instead. Okay. Yeah. There's no reason for this example to be here. I just need to delete that. Whoops. I guess I have nothing more then. Which is good because we're running a little low on time anyway. I might not have finished it. So. Questions about any of these? All right, we'll do planes next time.
All right.
I'm glad I checked it out before I actually did it.